Today we will discuss the Williamson synthesis. This synthesis is used for the preparation of symmetrical and unsymmetrical ethers. Symmetrical ethers are those where R and R dash both the groups are same, while in unsymmetrical ether the R and R dash both groups are different. Right? We have here two reactants. First one is sodium alkoxide. This is the sodium salt of an alcohol, and the second one is alkyl halide. Here the alkoxy group combines with the alkyl group of this alkyl halide to form the desired ether. Right? The side product is sodium halide. Right? Let us take an example. First one is we are using here sodium ethoxide. Right? This is the sodium salt of ethanol. The second reactant is ethyl iodide. This ethoxy group will combine with ethyl to form diethyl ether. Right. Let us take a view on its mechanism. This is SN2 substitution reaction where the alkoxy group O negative of this alkoxy group attacks on the alkyl group of alkyl halide to form the desired ether. Now the question is that why do we use always the sodium salt of alcohol and not the alcohol itself? The reason is that the attacking species, that is O negative, here the attacking species O negative which attacks on the R or carbon of alkyl halide, and in case of alcohol the lone pair will attack on this carbon or on this alkyl halide. Right? Among these two, this O negative which contains direct charge, this is more nucleophilic in comparison to the alcohol which is not having any charge on it. Right? So to increase the nucleophilicity of alcohol, we prepare its sodium salt so that the reaction takes place in a minimum time and with maximum yield. Right? But this reaction has some limitation. First one is whenever we use the halide, we always use the alkyl halide. I have written here alkyl halide, not the aryl halide. Right? We can't use the aryl halides in this reaction because these aryl halides are resonance stabilized, and due to which this carbon and bromine bond gets the double bond character. Right? As we have written here, the phenyl bromide group, here bromine has 3 lone pairs and its lone pair will participate in the resonance. This carbon bromine bond will be double bond and this carbon will get negative charge. Also these further structure have carbon bromine double bond. So this what we can say as aryl halides always have partial carbon halide double bond, and as we know double bonds are difficult to break in comparison to the single bond, so we can't use the aryl halides in case of Williamson synthesis. We always take alkyl halide in the Williamson synthesis. Now let us take the example of phenitol. This is the common name of this ether, phenitol. We can have two different reactants in this case. Like either we can have sodium ethoxide, this sodium salt ethoxide will be given by the sodium salt, and this phenyl group will be attached to some halide, that is some halide, aryl halide. Either we can have the aryl halide and the sodium ethoxide, or we can have sodium phenoxide, sodium salt of this phenol, and the other would be C2H5 Br or chlorine or iodine, anything. Right? We can have this alkyl halide, that is either we can took this alkyl halide or we can have the aryl halide. But as we have studied that we can't use aryl halides because this carbon bromine bond will have the partial double bond character, so it will be difficult to break this bond, so we can't prepare phenitol through this mechanism, or we have to take sodium phenoxide and ethyl bromide or chloride or iodide etc. to form phenitol. And the second drawback is that the alkyl halide which we are using in this Williamson synthesis should be primary always. for getting a better yield and better result, we should use a primary alkyl halide in comparison to secondary and tertiary alkyl halide. If we are using secondary and tertiary alkyl halide, then we would get the elimination product as major one and the substituted product as minor one, or we will get only the elimination product. Elimination product is the alkene, right? Here we are taking the example of tertiary butyl ethyl ether. If we want to prepare this ether, then we have to take the primary alkyl halide, that is ethyl halide, or we can take the tertiary alkyl halide like this one, that is tertiary butyl bromide. But in case of tertiary butyl bromide, this carbon is sterically hindered. This is so much sterically hindered that the the other alkoxide ion will not attack on this carbon. Instead, it will abstract the proton from this carbon, and the alkene product will be the major one, and the sodium ethoxide will form the ethanol as side product. So to prepare this tertiary butyl ethyl ether, we have to take primary alkyl halide, that is ethyl bromide. Here we are using ethyl bromide because this carbon is least sterically hindered in comparison to this halide, where this carbon is tertiary and is highly sterically hindered. So to prepare tertiary butyl ethyl ether, we can't use this tertiary halide. We will use the primary alkyl halide, and the second part is the sodium butoxide. Here this O negative butoxide of this sodium butoxide will attack on less sterically hindered carbon to form the desired ether product.